Hello and welcome to another episode of CTEX Tips and Tricks. In this episode we're going to focus on only one subject, and that is being able to compute the thickness of a geologic layer after a Surfcut operation. Now this would be useful in many situations. Examples would be computing the thickness of a geologic layer above or below a water table, the remainder of a geologic layer after excavation. So for all of these cases we need to use MVS's Surfcut module, and in the application that you can see on the screen right now we actually need 2 copies of it. So though you may think that after a Surfcut operation that the thickness data that remains would be representative of the remaining surface, that is not the case. So we're going to walk through the process of what it takes to get there. Now I've got a geologic model. This is one of the standard data sets that comes with our software, and I've actually manipulated a fault surface so that the surface passes through one of the geologic layers. So in this case it's the 4th layer in the model, and the surface is complex as is the layer, and the cutting surface is not continuously inside the layer. It passes out of it, and that complication is part of the complexity of this application. So for a starting point, I'm going to turn off all of the layers except for the one that we're dealing with, and I've done that in Explode and Scale by just turning off all these layers. Remember, you need to turn off the Use Entire Model toggle so that you do have the ability to control which layers are visible. And again, you can see our cutting surface is for the most part inside of this layer, but then on the right side to the east it is passing above it. Now to get the either the top or bottom of the layer above or below the cutting surface, we run Surfcut. So I'm just going to run it now, and it is nearly done. And at this point we can look at what remains of the layer. So right now we're cutting below the surface, and with Surfcut there is a toggle to reverse the cutting surface normal. So if I flip this, we'll get the opposite. We'll get above the cutting surface. In the intersection module I have 2 subsetting operations. The first one is Surfcut, and it's above 0, so it's giving me all values that are positive, and we want that. So if you get the wrong side of the surface, change it with Surfcut by reversing the surface normal. And then I also want to get rid of any parts of the layer that are below some threshold thickness so that I'm not seeing the pinched out regions of the layer. Now right now I could color this layer by thickness, but you need to be careful because that is the original thickness. In other words, the data that passes through from 3D geology map, that is the layer thickness, is not affected directly by Surfcut. So this data is the original thickness and is not representative of what remains after this cutting operation. You'll notice that we've got the output of intersection, which is this volumetric remainder of this layer, passing into the leftmost port of Krieg 2D. And we haven't run Krieg 2D yet. We're not quite ready to do that. But the leftmost port, figure out what the ports mean, you can find out by clicking on Info, is the external grid port. And the rightmost blue-black port is the external data port. So what we're going to do with Krieg 2D is we're going to map data onto this volume in a 2-dimensional manner, meaning that it's going to be Z invariant. That will allow us to assign thicknesses that correspond to the XY locations but are invariant with thickness onto this once we get them. And we're going to get that true corrected thickness from the data passing into the right port. And so the rest of this application over here is designed to get us there. So let's take a look at what's in that application. First thing is that we have the geologic surface corresponding to the bottom of this layer. So if we are cutting a layer and we're keeping the bottom half, we want the geologic surface corresponding to the bottom half. If we're cutting and keeping the top, we want the geologic surface that corresponds to the top. So if I connect geologic surface to the viewer, you'll see that, let's turn off disconnect intersection for a second. You'll see that this is the surface that corresponds to the bottom of the layer. Right now this surface is probably colored by layer thickness, and it is the layer thickness that corresponds to this layer, since data mapping is to the bottom. So this was the original layer thickness, and still it's not the resulting layer thickness. But we want that surface. We pass that surface into Surfcut, and we're going to cut this surface with our cutting surface. Now, what does that mean? They don't even intersect. How can I talk about cutting a surface with another surface that doesn't intersect it? And the trick is that Surfcut doesn't do any cutting at all. Surfcut merely computes the distance from the cutting surface to the object to the objects that you're cutting. So in other words, the object we're cutting is the left port, the cutting surface is the right port. The data coming out that will be assigned to this surface, the lower surface, will be the distance from any point on that surface to the nearest point of the cutting surface. And so that distance is effectively the thickness of what remains. So after we run Surfcut, let's go ahead and run it now. We then pass Surfcut into data math, and Creek 2D ran already, so I'm going to disconnect it for a second while we keep talking about what we have here. Surfcut passes into data math. It also passes into the slope and aspect module. So let's take a look at that one first. Slope and aspect gives us cell data for every triangle cell in the grid, corresponding to the slope of that surface. Now, I said a minute ago that the thickness that we compute will be the thickness, it's actually in this case the normal thickness, the thickness perpendicular to the surface. When we compute thicknesses normally for geologic layers, they're computed the way that most geologists would report them, which is along the direction of a vertical boring. So that thickness from the cutting surface to the bottom of this layer in the vertical direction can be determined by taking the normal thickness and dividing by the cosine of the slope of the surface. So now in data math, that's what we're going to do. We're going to take the Surfcut, which is our normal thickness, and we're going to divide it by the cosine of the slope. We have to convert that angle, which is reported in degrees, into radians, because the cosine function uses radians. So this AN0 divided by the cosine of our slope angle times pi over 180 would be now the corrected thickness in the vertical direction. And then the one last thing we need to do is report either that value or the original thickness, whichever is less. Now the reason for that is wherever we haven't cut the surface, the original thickness is the correct thickness. Wherever we have cut the surface, this value will be less than the original thickness. So the minimum of these two will be the true value that we want. Now, the one other thing we had to do with slope and aspect was, since slope and aspect is cell data, we need to convert it to nodal data, which you'll notice sort of smooths it out because we're doing all these computations on a node by node basis. And you can see here that our slopes are 0, lowest where the surface turns and goes horizontal, and they're steepest down here where the surface makes a turn and cuts downward. So finally, now the output of data math is a surface corresponding, this surface, bottom of the geologic layer, corresponding to the true reported final resultant thickness. And if all we wanted was a surface with that data, we're done right here out of data map. But if we want the volumetric result, we pass this into Creek 2D. We want to make sure that under data processing that we're not doing log processing and we're not clipping data that might be negative, so I just unintentionally gave it a small value here. And then when we connect this, let's disconnect the slope surface, we now have our resulting thickness that is 24 feet thick in these hot spots that are kind of little bumps here on the back. So you can see where this made a thicker region because our cutting surface has little humps in it. And pinches off to 0. Doesn't exist where the surface is pinched out. And so this is the true corrected thickness that we end up with. Hopefully this made sense. I understand that this is a very complex subject. This application will be available for download, and the reference will be in the link in the message here in our YouTube. Thank you for watching this additional episode of CTech Tips and Tricks.